Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. If you step on inside, you big ideas math, integrated math 2 folk, we are doing the Chapter 6 review, the one officially from the textbook, not the Are You Ready worksheet one, which I thought was actually pretty good, and it covered some things, not section 6-7, and this one should cover section 6-7. I saw there were 20 questions on this one. If you check out the timestamp, the description section below, you'll find timestamps to each problem that I do. If you know these textbook reviews, you know that there are examples before, which I can just lead into or talk about a little bit before leading into the actual problem sets that they do. They do these in order from 6-1 to 6-7 as well. I can do very little teaching as I go. I kind of want to do the problems a little more, so it depends on on what there is. I've done videos for all of 6-1 to 6-7 that are either an hour long or 3 hours long, or whatever in between. But guys, let's go ahead and get started here. Let's start and let's look at section 6.1 in proving geometric relationships. This is literally involving proofs. Okay, so that's what we are covering with this stuff here. Now, when you look at the stuff that they have highlighted here, this part A, rewrite the 2-column proof into a paragraph proof. And I don't know if that's what we're going to be asked to do. I haven't looked at our problem set ourselves. They show you a 2-column proof. We'll talk about what it looks like and how the paragraph proof is a version of that here. So in this 2-column proof, they have this figure. They show that given angle 6, let me see if I can get this pen thing up. Given that angle 6 is congruent to angle 7, so these two things are congruent as given, and we got to prove that 7 is congruent to 2. Pretty straightforward because 6 is congruent to 2 because they're vertical angles, lines opposite each other that intersect. You have what's called the transitive property of congruence, and my markings kind of show that. 6 congruent to 7 single arc marks. I can make 6 congruent to 2 with the same single arc marks. If 7 and 2 share single arc marks for that reason, the transitive property of congruence says two angles congruent to the same angle are congruent to each other. If 7 is congruent to 6, and if 2 is congruent to 6, then 7 and 2 must be congruent. That's the 2-column proof version of it. The paragraph proof thing is basically just giving sentences with those. And in a single sentence, they're going to use the statements and the reasons together. So for example, angle 6 and 7 are congruent. They don't say that it's given. They're just telling you a fact, something that we do know that's given. By the vertical angles congruence theorem, 6 is congruent to 2. Reason, statement. Kind of, it's just in English, they'll say it that way. By the transitive property congruence, 7 is congruent to 2. You can say it the other way. 7 is congruent to 2 by the transitive property. But you can see that translation. And maybe we're going to be asked to do that. I have no idea. Write a coordinate proof. So these ones can get a little cumbersome sometimes, but what's nice about them is often you get to, for a triangle, for example, lay one of the sides down flat against this x-axis. That makes heights and numbers really easy to work with. What's the distance between 0 and c? Just c. The heights of 0 and 0, the difference is 0, and that makes it really easy that way. What are we going to do with this? Given coordinates of vertices OAC and BAC. So given this drawing with A being what it is and C being what it is, etc., prove the triangles are congruent. So their proof, they're going to do one of those side angle side kinds. It looks like they literally did side, side, side. But they do one of the proof things. They're showing that all three sets of sides are equal to each other. AC is going to be congruent to itself by the reflexive property. The distance from 0 to c over 2 is literally c over 2. From c over 2 to c is also literally c over 2. They show you that. And then they got to use Pythagorean theorem or distance formula to come up with the distance here. It looks like it is 1/2 c root 5. You can look at the work, but both of them are 1/2 c root 5. Therefore, they're congruent. Triangle congruences can come in many forms: side, 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 angle, side, angle, 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 side, and HL, all depending on what you have. They could have proved HL if they talked about, not HL, well, they could have shown these are right angles, but that would have taken a lot more stuff, opposite reciprocal slopes and the like. I think they were good in just showing distances that they had there. So there's a congruence proof there, and I haven't mentioned this much because we haven't done a lot in triangle congruence. You have to make sure that you put the corresponding parts in a certain order. OAC is congruent to BAC. O and B, this is kind of a reflective triangle thing. It's like my hands. O and B are corresponding points. A corresponds with A in both triangles, C with C in both triangles as well. Okay, let's go ahead and do our problem set. Why don't we, huh? Let's go ahead and look at number 1. Use the figure in part A. Write a proof using any format. I'm likely going to do 2-column proof. Where's A? Oh, the first one. Okay, let me get rid of this stuff here. So let's copy and paste that thing over so I can use it and mark it up as I'd like to. So same figure. Let's see what they have written. And I'm going to go, like I said, 2-column proof. You feel free to go along with me here. And let's see what the heck we're doing this about. Because I don't think we're using the same given stuff. We're kind of doing some new stuff here. Statements, reasons. Why not? So yeah, section 6.1 was all about these proofs. I don't remember how long my video was for it, meaning I don't remember how many questions there were, just kind of how long it took. I guess I'm glad I've gone through all of it already. But now I'm back. Use the figure in part A, read proof using any format. Given angles 5 and 6 are complementary. Okay, so angle 5 and angle 6 are, I'm just going to put comp. So that's a given. Now, is there another given? There is a second given. It says 5 and 7, measures of angles 5 and 7 add to 90 degrees. That's also something that complementary mean. Now notice that 5 and 6 are adjacent with each other. That is not a requirement for complementary angles. And if you don't know what complementary angles are, it's not congruent. It's not that they're the same. They could be. But it's not that they're the same. It's that they add to 90 degrees. Just like the next one, 5 and 7 also add to 90 degrees. So here's what I'm going to put actually first. Because they're telling you they're complementary, we can then go back and say that they add to 90 degrees as well. They're measures. That is what complementary angles are, and they do not have to be adjacent. Definition of complementary angles. So that's the way that I can reason with that, right? Because they told us this, we can then make that statement. Now, they also told us that the measure of angle 5 plus measure of angle 7 is 90 degrees. That was also another given. Generally, you would write givens first, but because I wanted to lead statement 1 into 2, I just went about it this way. Now, what are we proving? I didn't check. 6 is congruent to 7. Okay, we're almost home. So right here, what I'm going to do is now say, notice how both of these add up to 90, or they equal 90. Two things that equal 90 must also equal each other. So that must mean measure of angle 5 plus measure of angle 6 is the same thing as measure of angle 5 plus measure of angle 7. Now, we saw something kind of similar to this when we said angle 2 is congruent to, what was it? Oh, I have the diagram here. 2 was congruent to 6 and 7 was congruent to 6. Therefore, 2 was congruent to 7. That was known as the transitive property of equality. Two angles congruent to the same angle are congruent to each other. There's a transitive property of equality as well. Sorry, if I said equality the first time, I meant transitive property of congruence. Transitive property of equality also exists. Two measures equal to the same measure are equal to each other. Now, we need to prove angle 6 is congruent to angle 7. And as you notice, this says 6 on this side, 7 on this side, and they both share a measure of angle 5 added. What if you subtracted the measure of angle 5 from both sides and it was gone? Literally, it's like subtract x from both sides or subtract 5 from both sides. And now you have measure of angle 6 equals measure of angle 7. I literally subtracted 5 from both sides. That is my reasoning. I'm going to say subtraction property of equality. Now, these are phrases that I guess you're going to have to learn over time. If you reasoned and said, I subtracted measure of angle 5 from both sides, I think most of us see what you're doing there. The properties of equality are ways of saying that you can do things to equations and both sides of them and maintain some form of balance, specifically the subtraction, addition, multiplication, and division ones. Now, they want to say angle 6 is congruent to angle 7. Notice what I'm doing here. I'm going from the values, the abstract version of these, the numbers, whatever the measures of them are, they could be 32 degrees each. Now we're just saying that their objects, their physical parts are equal to, or are congruent to each other. And that is, it's called the definition of congruence, that equal measures of angles means that angles are congruent. Definition of congruence. And that would be it right there. So I actually started in a physical sense with the first given as well when they said they're complementary. Notice I went from physical to numerical value as well, and then we came back to the physical. Let me take away what I put there for those slashes. You're not supposed to slash them out. That's part of your statement. All right, that is number 1. I'm comfortable with that one. Number 2, use the figure at the right, write a coordinate proof. So let's go. Coordinate proof. Okay, so this is not a 2-column thing, but let's borrow this. It always comes blurry on this end because it blows up, so I hope shrinking it just sharpens it, makes it look a little better. What are we proving? Coordinates. So given the coordinates, prove that it's isosceles. Okay. In order to prove an isosceles triangle, An isosceles triangle by definition has two congruent legs, just two sides of the triangle are congruent, and then their angles opposite those sides are congruent. I don't think we can do much in I don't know if we can do much in the form of angles, so we'll just deal in the form of the sides. It looks like we're going to show that this side is equal to this side in terms of length. And listen, they talk about this distance formula stuff. I'll go ahead and give you those distance formula things as well for a brief moment, such as let's find the distance from O to C. O to C, that's the square root of the x's, the difference in the x's squared, a minus 0 squared, plus b minus 0 quantity squared. So that's the square root of a squared plus b squared. Now, you cannot turn this into like equals a plus b. No, that's not how you take square roots of things. We're going to have to leave it like that. Now, the distance from O to B, or the length, is the square root of, now we have negative a minus 0 squared plus b minus 0 squared, quantity squared. Now, negative a minus 0 is negative a. But negative a squared is still a positive a squared, if you know what I mean. Squaring a negative turns positive. So that's still a squared plus b squared like that. So they are the same. Same length. So OB is the same thing as OC. Therefore, triangle OBC is isosceles. So that was a small one. Now, I did do their distance formula. It's not theirs, but I did use the distance formula the same way that they did. Distance formula is nothing more than some version of Pythagorean theorem. And if you want kind of proof of that, well, not proof of that, but if you want an indication of that, what I really would have loved to do is say, what's the distance from 0 to A? I mean, that's what you do when you subtract, but you can count that out as well. And this distance is B. In Pythagorean theorem style, it's a squared plus b squared literally equals the c squared right there. Take the square root, you get that number. And the same thing here. This distance here is also a and b, or negative a, doesn't matter. But the point is you get, oh, I have this backwards anyway. This is a and b. But anyway, yeah, at either rate, depends on what we're going to have later. I'm really big on just drawing on my graphs and using those right triangles. Sometimes it kills two birds with one stone, and you get to work off those slopes and do some things as well. But that is number 2. So pretty basic overall. That one was pretty basic overall. I hope you enjoyed the construction of that one and got a feel of what we're doing in that section. All right, we're going to work section 6.2, and 6.2 and 3 are really in cahoots with each other. 4 kind of is as well with those, and then 5 and 6 kind of do their own thing. Perpendicular and angle bisectors. Now, there are 2 theorems and their converses, the perpendicular bisector theorem and angle bisector theorem. In a perpendicular bisector situation such as this, AC perpendicularly bisecting BD, this point A is equidistant to the endpoints B and D of that segment. So you can set these two equal to each other. 4x plus 3 equals 6x minus 9. You do the math, the algebra to solve for x, and you get 6. And then they want the length of AD. So you substitute 6 into AD's expression. 6 times 6 minus 9. 36 minus 9 is 27. That would be the length of AD. In part B, you have what's called the converse of the perpendicular bisector theorem. If you have a point that's equidistant to endpoints of the segment, that means that point is on the perpendicular bisector of that segment. Now, we know that these are both 10 apart, or H is 10 apart from G and E. H is on the perpendicular part here, therefore it is also, this HF is also bisecting this. So if this is 6, so is that. Now they say, what's the length of FG? I guess that's going to be 6 as a result of that. They could ask for EG, and you double it, but they didn't, so we don't. LM is all about the angle bisector theorem. Oh, and notice they're actually asking you to, they're telling you which thing here. So perpendicular bisector theorem, converse of the perpendicular bisector theorem. This is the angle bisector theorem where JKL, angle JKL is bisected by KM, its angle. So those two angle measures are congruent. A point on an angle bisector is equidistant from the sides of the angle. And we go by shortest distance. Distance from point to a line, the shortest distance is the perpendicular one. So we know that those are the kind of same relative points we're referring to. Anyway, these would be the same. 8x minus 15 and 3x. You set them equal. Solve for x. Find the length of LM. Substitute 3 in there. 3 times 3 is 9. If they ask for angle measures, make sure you put the degrees. If they had inches or something, you would put inches. Finally, part D. This is the converse of the angle bisector theorem. It shows right there. A point that is equidistant from the sides of an angle is also said to be on the angle's bisector. So z is 8 units away from the shortest distances here, z, x, and zy. So z is on, or wz must be an angle bisector, therefore. So we're going to find the measure of angle xwz right there. This is a bisected angle, therefore if that's 46 degrees, then so is this one right here. So they're both 46 degrees. That's why I have to put the degree symbol. There we go. All right, those are the examples. Let's go to numbers 3, 4, and 5. Now that I've kind of explained all the things that they put there, we can go straight into these pretty hard and pretty fast. I'm going to let the drawings be where they are and use what you need to find. Find the indicated measure, explain your reasoning. I'm going to use the converse of the perpendicular bisector theorem. I can see that perpendicular portion and B is equidistant to both points A and C. Therefore, BD is on the perpendicular bisector, which means this part's being bisected. AD is equal to DC. AD is equal to DC by the converse of the perpendicular bisector theorem. I'm just going to kind of put it short. Short and sweet. So 20 equals 7x minus 15. Now, I don't even know which one we're solving for. I just know that we can set this up and we're going to solve for x. Add 15 to both sides. Divide both sides by 7, you get x equals 5. Now, we're not done, I don't think. Nope, we got to find the length of DC, which is 7x minus 15. Here's the thing. I didn't need to do any of this solve for x to find the length of DC. If AD is 20, then DC is 20. Maybe I should have looked at the problem first. Because, listen, they're going to be the same thing. But I guess we're proving our point with it that this is going to work. 7 times 5 is 35. 35 minus 15 is 20. It's going to be the same as AD. I literally didn't have to do anything because they gave us a full expression for AD. Number 4. Let me move this guy here. Let's find the length of RS. And first, let's make sure that we have to do something. It looks like we do. We're going to use the angle bisector theorem here, the same way that part C used the angle bisector theorem. That S is equidistant to points P and R on the sides of the angle, of the bigger angle. So SP is the same length as SR by the angle bisector theorem. So I can set 6x plus 5 equal to 9x minus 4. Subtract 6x, add 4. Divide both sides by 3, you're going to get x equals 3. Let's find the length of RS. Let's substitute 3 in for here. 9 times 3 is 27. 27 minus 4 is 23. And number 5, let's find the measure of angle JFH. It's one of those things again where, oh, never mind. I thought there was an algebra portion. I was going to say it's one of those things again where I could just say what it is. Was one of the examples like that? Oh, okay, like this one. Yeah, perfect. Listen, it's 47 degrees. Given they want a reason though. So measure of angle JFH is the same thing as the measure of angle JFG by the converse of angle bisector theorem. Therefore, the measure of angle JFH is 47 degrees. Don't forget the degree symbol. Okay. We're good to go. A lot faster than the proofs, huh? Let's look at section 6.3 on bisectors of triangles. Oh, that's right. We have to do some graph things. I think I still have my graph paper stuff with me. It's good. I'll attach that as well if we need to. Find the coordinates of the circumcenter of triangle QRS with vertices Q, R, and S as follows. Okay, so they're going to talk about midpoints and such. They didn't seem to calculate the midpoints for you. So I guess they're comfortable with us finding midpoints in our own way. So QS, oh, maybe not. From Q to S, the midpoint here is at 6,3. It's literally the halfway point. If you're at the same height here, you just got to count 6 away. Half of that is 3 away. And same thing from Q to R. I can go, instead of up 4 over 2, you go up 2 over 1, and bam, you hit that midpoint right there. So all about midpoints, you can either average your x's and y's of your 2 points, or you can count half the distance of your x's and y's, and you will land on the midpoint. They didn't seem to show any work here, so I wonder if we're going to do that. Now, they do talk about the equations of the lines. They say find the coordinates of the circumcenter. I'm probably not going to get as deep as the equations of the lines, and since they didn't show work for that either, I guess it means that you probably have to get a lot more work. But what you do need is you need to strike through your midpoints here. Notice how these red lines strike through the midpoints. And you need to draw perpendicular bisectors. To get perpendicular lines, you have to know how you find them on graphs. It's all about the slopes of those lines. Now, the easy one to talk about, whether you want to talk about slopes of lines or not, this is a horizontal line, and perpendicular to a horizontal line is a vertical line. Period. Just draw a vertical line through that, you'd be good. However, this one is some sort of diagonal line, but it has some sort of slope. You mentioned, or you didn't. You heard me mention we went up 4 over 2. Well, that slope is 4 over 2, or 2 over 1, I'll just say. And then the opposite reciprocal slope, you flip the fraction to 1/2 and you change the sign to negative. That's why they're showing this negative 1/2 x plus 7 kind of equation. That slope, down 1, right 2, down 1, right 2, down 1, right 2, that's the opposite reciprocal slope that makes this a perpendicular line. So that's what we're going to do, guys. We're going to come up with perpendicular lines through the midpoints of segments. That gets us perpendicular bisectors. And you only need to draw 2 of them. Any 2 of them will be at your circumcenter of your triangle. And if you don't know what a circumcenter is, it is the center of a circle, which you could circumscribe about a triangle, like so. If you see when I draw this thing here, all these guys are supposed to, depending on how I make the center. Because it's really drawn to scale, right? This is on a graph. Kind of look like that. It hits the triangle at these vertices right here, that circle, which means the distance from this circumcenter to the vertices are all the same because, as you know, a circle has radii. And that's something we can probably use for other problems. Anyway, that's one example. Circumcenter is at 6, 4 is what they found. In the second example, and only the second example, they have an in-center. Section 6.3 is all about circumcenters and in-centers. An in-center, by the way, well, let's see what I want to answer. Okay, an in-center, by the way, is a center of a circle which can inscribe a triangle. That means you could draw a circle on the inside and touch all the sides of the triangle tangentially, which means those things, you see where those right angles are? Those are the shortest distances to the sides, and that's what the circle is actually also going to hit. These are all the same distance as the circle's radii. These are all going to be equal in length. And that's what they're kind of doing. Point N is the in-center here. ND is 4x plus 7. This is ND. NE right here is 3x plus 9. They're the same. That's why they set them equal, and they solve. They say find the length of NF, which is the same as those two. So when they solve for x, they can substitute into ND's or NE's algebraic expression. That means if one of them's 15, so are all the others. They're all 15. And that's where we're going from there. So let's go ahead and jump right into it. Notice they actually didn't do any graph ones for in-centers because, believe it or not, I don't know how to draw angle bisectors of things on graphs generally. I really I got to look at it and think into it, but since they don't have any problems on it, it's not as easy to divide things in half when it comes to slopes. You really have to think on how that works. It might be easy, but I don't think on it very often. Anyway, number 6, find the coordinates of the circumcenter of the triangle with the given vertices. It has nothing to do with this part, by the way. We're just plotting these points here. So T is at -6, -5. I'm going to get a bigger version again, as long as you can see all that. T is at -6, -5. U is at 0, -1. And V is at 0, -5. Now, I wasn't really able to mention this in the notes part because of the kind of triangle it was, which was an acute triangle, and the circumcenter was inside the acute triangle. This is a right triangle. Circumcenters are on right triangles, and you'll kind of see why when we draw stuff with it. So remember, a circumcenter is made from the perpendicular bisectors of a triangle. Horizontal and vertical lines are easiest places to find midpoints and to draw perpendicular lines. The midpoint from T to V, this distance is 6, so half that distance is 3. Guys, I have my midpoint. I'm not going to spend more time calculating it than I need to. This distance is 4, half that distance is 2, so this is that midpoint. Now for each individual midpoint, we want to draw a perpendicular line through them. And perpendicular to a horizontal line is vertical, like this. This is like the entire angle bisector, if you will, going way through. and then the entire angle bisector here goes way through. These are two of the three. If I said angle bisectors, I meant perpendicular. These are two of the three perpendicular bisectors in this drawing. There would be a third whose midpoint would literally be here, part of the concurrency of all the perpendicular bisectors. And then you'd have to find the opposite reciprocal slope of this guy. I'm going to make one up that's kind of like that. Hey, they're perpendicular. But the point is they're all still concurrent at this single point. So getting rid of that, this single point is your answer. This is your circumcenter. It is on the triangle. So that guy right there, which is at -3, -3. So circumcenter at -3, -3 on the triangle. And it would be on the hypotenuse. Hypotenuse is on that midpoint, all that kind of stuff. That is number 6. Number 7, let's do it again. I think, right? Yeah, find the coordinates of the given vertices. I think that's just for 6 and 7. I think 8 is a way different question about that diagram right there. So number 7. Number 7, let's do the same kind of thing. Hopefully it's not a right triangle again. And you know, I really hope it's not. My previous review thing that I had was only right triangles for circumcenters. We need to get off the right triangles. Let's go to x at -2, 1. Y at 2, -3. I always have to look at where I need to write these letters before I do them. And Z, good, I don't think this is a right triangle. And Z at 6, -3. Definitely not. Totally obtuse. Totally an obtuse triangle. And with that said, you have seen an acute triangle in the example. The circumcenter was inside of that triangle. In a right triangle, you saw the circumcenter was on the triangle. In an obtuse triangle, it's outside of the triangle. Now, one of the easier perpendicular bisectors to draw is one I will from Y to Z. You can find the midpoint halfway in between like that. And again, it's a horizontal line. Perpendicular to it is a vertical line. So I'm going to go ahead and draw one of those. You really want to extend these out because maybe you don't know which direction these things are going to go. But circumcenter is outside of this triangle here. Now, let's do it for one more point. And the easier one would be from X to Y. I'm going to work more from X to Z because I want to speak more on perpendicular bisectors and stuff. First of all, we're going to have to find its slope. So I'm going to go ahead and do that count right now anyway. Let's use just a purple color for now. How much are we doing a rise and run or that kind of stuff? So from X to Z, or Z to X, let's say, we're going up 1, 2, 3, 4. And then we're going left 1, 2, 3, 4, 5, 6, 7, 8. So left 8. So the slope of segment XZ is 4 over -8, which is -1/2 when reduced. However, before I move forward with that, this is my kill two birds with one stone kind of thing. I want up 4 or left 8 to go from Z to X, but we need its midpoint. So let's go up and over half of that. Let's go up 2 and left 4. This point right here is the midpoint of this one. 2, -1. I didn't average my X and Z values. You could have averaged my X and Y values of points X and Z. You would have gotten and landed on that point right there. I'm really using the graph more so. But this slope is still going to help me because I still need to make the perpendicular line that goes through this. And the way to do it is to find the opposite reciprocal of this. -1/2's opposite reciprocal is +2/1. That is the slope. And I'm not getting the full equation, but I need to rise 2, run 1, rise 2, run 1. You can see where we're going to land there. That's going to be the answer. Rise 2, run 1, etc. Now, I did it with this segment right here. The reason I said X, Y would be easier to work off of is because it has a slope of just -1, -1/1, but you don't get to see the effect of flipping your fraction over. So I really wanted to show it with this one here. That's maybe a little more bold and challenging and stuff. But they'll all land there is the point. The circumcenter is outside of your circle this time. It is this one right here, y'all. This is your circumcenter right there. It is at 4, 3. So circumcenter is at 4, 3. Now, to remind you what a circumcenter is, I probably should have done with the other problem, but I still can. Circumcenter is, do I draw circles? Yep. The center of a circle that if I draw, in this case, if I draw it to the vertices, it will hit all the vertices of your triangle. So check out how it hits X, Y, and Z. That means X, Y, and Z are all the same distance away from that center. This distance, this distance, and this distance are all the same. In this other triangle here, when I draw this one out, same kind of way, U, V, and T are all, without snapping there, are all the same distance away from this circumcenter. This distance, this distance, this distance are all the same thing. Doesn't look like we're really doing any problems with those, and you're not required to draw the circle, by the way. You're just trying to find the circumcenter itself. But looks like we're not really doing any problems with those ones because we're jumping to incenter. Number 8, point D is the incenter of triangle LMN. Find the value of X. So we just saw incenter before with the thing above. That makes all these distances the same, as opposed to circumcenter where it's equidistant from the vertices. This is equidistant from the sides. They said find the value of X. Our dr is, well, X. Dr is going to be equal to dt. This is the, this is kind of the angle bisector theorem in a way. Dt here. And therefore, X is 5. I'm over speaking on the problem. I wish they asked us to do more. Like find this length here, which by the way would have been 12. Or the whole length here, which would have been, you can't assume that's 24 actually. But, yeah, that was it. X is 5. Okay, let's keep moving. All right, section 6.4 is medians and altitudes of triangles. Now, there are a lot of words you're going to be hearing here, and I hope this isn't the first time you're hearing them. We just talked about perpendicular bisectors and angle bisectors to find circumcenters and incenters, respectively. Now we're going to be using medians and altitudes to find centroids and orthocenters, respectively. And trust me, if I go a year off teaching this and go back to it, I'm going to kind of forget some of these words exist. Not literally, but it's one of those things that if you don't remember going out of this terribly, it's not the worst thing. Just learn it as you're doing it, understand what you're doing with them. These have greater purposes. Not every single part, but you use some of these for greater things later. Altitudes are a huge part of math that you do all the time, man. Areas of triangles, all the time, 24/7. It's just a big part. All right, medians give you centroids, and a centroid, which, let's see how they, they do the 2/3 thing. Okay, a centroid has a very specific relationship when you get all those medians drawn together, because you could draw more than just this one right here. For example, maybe this could be one of the medians here. And a median, by the way, is the segment drawn from a vertex to the midpoint of the side opposite that vertex in a triangle. So for example, maybe these are the other two medians. That would only make sense because it goes from vertex and through the centroid. All of these ones right here have a relationship where the distance from the vertex to the centroid is 2/3 the distance from the vertex to the midpoint, that opposite side. So this is 2/3 of that. This is 2/3 of that. And this is 2/3 of that. Which also means this is 1/3 of the whole thing, 1/3 and 1/3, which also means the short guy is half the size of the bigger guy right there. Stuff like that. So if you've seen all that before, awesome. Let's go ahead and see what they want to do with this stuff and how they tell you, that the answer is what it was. This is the only example. So we're finding the coordinates of the centroid. They went for the easiest one. When I drew those medians, they were like right in between these weird numbers, so it was good that they drew this one. They found the midpoint opposite this vertex U at W. This is where they show averaging X's and Y's to get them. You saw what I was doing recently, just count kind of the slope and go half that distance. If this is over 6 up 2, go over 3 up 1, and bam, you got it. And honestly, I'm going to probably do more of that still. So they find that midpoint at 4, -7. You can see that it's vertically straight down from U, which is really good because that whole 2/3 thing applies here. 2/3 the distance from U to W. This distance is 6. So 2/3 of 6 is 4. So just go 4 down from U, and bam, you're going to land on P, what is apparently the centroid. You could draw another midpoint and then therefore another median, and then see where those are concurrent as well. Either or is fine. They found it at 4, -5. We're going to be doing the same, so let's go ahead and do so. Let me start it on another page, actually, number 9. So let's go to points A, B, and C. A is going to be at -10, 3. It's always as long as it fits on the graph stuff, we're good. B is at -4, 5. And C is at -4, 1. So I think we're going to benefit from one of those. We can draw it straight through horizontally and vertically again, which is always a good thing. I think they don't want to hurt us in that way, but they could. They could. Again, midpoints, as long as you can find midpoints. And I'll draw all three midpoints for you. But first, let's do that 2/3 thing. Let's confirm that we can do this on our own, and then it'll all work out. The midpoint, oh, let's label this. A, B, C. Midpoint from B to C is halfway in between, like that. I'm not putting other letters right now. Well, actually, yes. Let's put D because I want to give them the names. So A to D is one of them medians. It's also a perpendicular bisector. That wasn't the point to do. I just did a segment was all, right? From vertex to midpoint. But it also is a perpendicular bisector. But, I mean, this is a bisector. That's the point. It is supposed to bisect it. Anyway, what's the distance from A to D? 1, 2, 3, 4, 5, 6. That seems to be a very common number that they choose, which is good because you can take 2/3 of that number cleanly. So the length from A to D is 6. And 2/3 from A to D is 2/3 of 6, which is 4. Now, if I count over from the vertex, not the midpoint, 1, 2, 3, 4, I have found my centroid right there. If I called it P the same way as they did before, centroid is that point P. That is at -6, 3. That would be the answer. Now, if you wanted to find some other points, let's put purple. If you wanted to find some other medians on here and see that they would be indeed concurrent with that, you might notice that the midpoint from A to B, it's up 2/6. So instead, up 1/3 would be that midpoint. And down 2/6, instead down 1/3 is this midpoint. So these two centroids would have been, medians would be from B to this guy and from C to this guy. I'm going to the green parts, and you can see that they all intersect there. So you can find other parts that intersect, and that's just fine if you're not comfortable with the 2/3 part. Both of them work. It's up to you. That one pretty fast with that, all told. Let's go to number 10. They didn't practice orthocenter in the example stuff, so I'll just make sure to talk about that even more so. So number 10, same thing to do. By the way, remember how we mentioned that circumcenters can be outside of a triangle or on a triangle? That is not the case for our centroids or incenters. It is true for orthocenters. We'll probably see one of those. I don't know. But it's not the true for these ones. It's not the case for these ones here because they're drawn from medians. Medians are always going to be inside of a triangle. So if they're concurrent at the medians, then, well, that's what you're going to have. All right, this looks like a right triangle, and this is just kind of one of those examples of how this thing might potentially work. The centroid won't be on the triangle. It'll still be inside the triangle. This might be an isosceles right triangle for that matter. I think it's one of those things that it's best that we just draw all the medians straight up and that you're comfortable doing so. Midpoints here are quite easy to find, especially at the vertical and horizontals. Half of 6 is 3. Boom, there's a midpoint. Half of 6 is 3. Half of down 6 over 6 is down 3 over 3. These are all the midpoints here, guys. And you know why you also probably want to do it this way this time? Because none of these medians are horizontal or vertical. So counting these directions and taking 2/3 of them is not fun. It's not fun for me. It's not fun for you. Not fun for anybody. Drawing any two of these three medians shows the point of concurrency right there. And mathematically, they're always going to still do that thing. So boom, let's actually do that in purple. So boom, that point P, again, is the median, the centroid, 4, -4. So your centroid is at 4, -4. And that's honestly the best way to do that one. 2/3 stuff. Because that distance isn't like 1, 2, 3. Well, you could kind of count that way and use it. It's not literally 3, but 2/3 of 3 of those is 2 of those. So you could kind of do that one. Anyway, let's keep moving forward. But there's your centroid. Okay, we're going to move on to number 11. Okay, so we're going to have tell whether the orthocenter of the triangle with the given vertices is inside, on, or outside the triangle, then find the coordinates of the orthocenter. Now, an orthocenter is made from our altitudes. We have G at 1,6. We have this guy at 5,6 right here. It's H. J is at 3,1. Looks like one of those isosceles triangle guys again, so fun. G, H, J. Inside, on, or outside is like the same as a circumcenter. Different parts of where they'd go because they're from altitudes, not perpendicular bisectors. Inside, an acute triangle. On, a right triangle. Outside, an obtuse triangle. This looks like an acute triangle. All angles acute, so this one will be inside of it. We can go pretty similarly to what we had last time. Now, this isn't about perpendicular bisectors. However, altitude, the altitude from J to GH will also be a perpendicular bisector, like this median was also a perpendicular bisector here. So this altitude will also be. How do you find an altitude? You got to find the slope of one of your sides, like GH is a horizontal line, so opposite reciprocal slope is a vertical line, and do it through the vertex, not through the midpoint, but through the vertex. Just so happens, though, through this vertex will also mean through the midpoint. So as long as they give you isosceles triangles like that, or equilateral triangles, those kinds of things happen. Here's an example of one of my altitudes. Now, I'd pick another one. This is isosceles. Let's just pick one out. Let's go from G to J. It's down 1, 2, 3, 4, 5, and over 1, 2. So the slope from G to J, or segment GJ, is negative 5 halves, and its opposite reciprocal slope, perpendicular line, therefore, is 2 fifths. So a slope of 2 fifths, what we're going to now do is take that 2 fifths slope and go from H, the vertex that will go through here, right? I want to do an altitude with that slope from H through GJ. So let's go from H, instead of going up to right 5, let's go down to left 1, 2, 3, 4, 5. Because my goal, my intent's to hit this thing here. Let's see how accurate this thing goes if I can line it up just with these two. Hopefully it just hits this vertex. From H to that guy right there. Nope, doesn't look like it hit something perfect. So we're going to have to do some extra work. But I'm a little bit blessed in two ways. The equations of these lines are kind of nice. This line, remember, this is a vertical line. And that vertical line, any vertical line is x equals some number. This one is x equals 3. Whereas this line right here, I know the y-intercept at 4, and I know the slope of 2 fifths. So this is the equation y equals 2 fifths x plus 4. Let's find out where x equals 3 intersects with y equals 2 fifths x plus 4. What's nice is x equals 3. I can substitute right into there. So y equals 2 fifths times 3 plus 4, which is 6 fifths plus 4 is also 20 fifths, which is 26 fifths. Now 26 fifths is 5.2, and that looks 5.2-ish. I'm going to leave it as 26 fifths, but the answer to your orthocenter, oh, by the way, I never wrote whether it's inside or whatever, but the orthocenter is at 3, 26 fifths. And by the way, that's inside that triangle. I think they kind of want you to say it beforehand, and I think I said it, I just didn't write it. All right, let's go to number 12. All right. K is at negative 8, 5. Okay. L is at negative 6, 3. Are we going to have an obtuse triangle? M is at 0, 5. Oh, that could be obtuse. K, L, M. They're nice to give us one of the things horizontal. Okay. Yep, looks pretty obtuse there. So my guess is this will be outside the triangle. Now, generally people have trouble perceiving, and sometimes I do too when I'm looking at it. I got to turn my head the right way. But we got to find a way to get ourselves an orthocenter. Now, do the altitude from L to KM. Remember, not a perpendicular bisector. You go from the point L literally perpendicularly through there. Because that's a horizontal line, I can go a vertical line right there. But I want more. I want more because mine is going to be outside of this triangle. Okay. I think it's going to be extending down this direction. Although you could draw both directions if you want to. Here's the right angle portion. and it goes through L, but go on the outside. Now, if you turn your head, I know on camera I'm turning my head the wrong way as far as looking at it, so I'll pretend like I'm doing it this way. If you turn your head the proper way, look at where KL is, but think about it so that LM looks flat to you, like a horizontal line when you turn your head like that. And when you do, imagine that you extended that horizontal line. I'm going to kind of do it faintly. Extend that horizontal line outward like that. Okay, just imagine that it's an extended line. You need to draw a right angle altitude from K through this horizontal, through this line right here. Remember, here it's something like that, right? I need the right angle of it. It's outside of the triangle when it happens. So we're still going to do the stuff that we did before. We need to find the slope of segment LM right here, which is 1, 2, 3, 4, 5, 6 over and 1, 2 up. So the slope of segment LM is, careful, it's 2 over 6, not 6 over 2, which is 1/3. The perpendicular opposite reciprocal slope to that is -3 over 1, or -3. So from K, I can go down 1, 2, 3, and right 1. That'll be that slope, and down 1, 2, 3, and right 1 like this, where I'm going to hit that point. I can even do it a couple more times if I want, but that will be my orthocenter, where those two intersect. Remember, all three altitudes would intersect there, but just these two at the very least is what I need. But this is perpendicular. From K through there is perpendicular to where this side would go. Remember, it doesn't have to touch the side. There are versions of it that can extend outside of it because it's an obtuse triangle. And so that's going to happen on this one. That's just what we get. But the orthocenter is this point of intersection right here at -6, -1. -6, -1. That's what we get. It's outside of the triangle. I didn't mention anything yet, and I can't really, about orthocenters and their math magic. We mentioned circumcenters circumscribe a triangle. It's equidistant to the vertices of the triangle. Incenters inscribe a triangle. They're equidistant to the sides of the triangle. Part of those two theorems we had, perpendicular bisector, angle bisector. Medians have the 2/3 distance from the vertex to the centroid as opposed to vertex to the whole median. This doesn't have those mathematical connections and relationships. It's not as fun to do more things with it. That's why they tend to ask orthocentered questions in this way. There are a lot more questions on medians they could have done through the sections they did. They didn't seem to here. All right, let's keep moving forward to section 6.5. We still have 3 more sections to go. Get ready for number 13 in a bit. But let's look at the triangle mid-segment theorem. And we're doing more on graphs, so it seems. It looks like both questions are going to be on them, and their example is as well. There's a lot more they could do with these as well. This is different stuff. 6, 5, 6, and 7 aren't as similar, except for in the graph department. But as far as finding centers, we're not doing that anymore. Show that the coordinates of show the mid-segment MN is parallel to JL and that MN is half of JL. Because that's what the mid-segment theorem is all about. A mid-segment is a segment joining two midpoints. A mid-segment is also parallel to the third side that it doesn't touch. That's part of the parallel part, but same slope is what you're going to try and find. It's also half the distance. So this distance is half the length of that one. So they're going to use their midpoints to actually find M and N, their formulas. I would just count half distances there. Draw a segment through it, what have you. Use those ordered pairs to calculate slopes. The slope of MN is 1/3. The slope of JL is 1/3. Same slope means the lines are parallel. Now they compare the lengths. They do their distance formula such and such. They get the square root of 10 for MN, and they get 2 root 10 for JL. 2 root 10 is twice that of root 10. Therefore, because of those two things, it is a mid-segment. So that's their confirmation. Let's do it here. It doesn't look like we have to justify things, at least not yet. Find the coordinates of the vertices of the mid-segment triangle for the triangle with the given vertices. You just need to find the midpoints of all 3 of these sets. And if that's it, that's not a lot of mid-segments. This doesn't really feel like a mid-segment review with those 2 questions. This just says find the midpoints of your things. And we've done plenty of that. Well, let's do it here. And I'm going to do it my magic way, not averaging my values. You can look at the formulas there as much as you want for it. A is at negative 6, 8. B is at negative 6, 4. And C is at 0, 4. Looks like a right triangle. That doesn't really matter for these. We're going to draw the midsegment. Don't get me wrong. We're going to do all that, but it looks like we don't have to do all the proof stuff, that how they are. So hopefully those examples are sufficient for you if you have to answer kinds of questions like that later. But midpoints, yes. On horizontal lines and vertical lines, my favorite. Not even being sarcastic. Half the distance from A to B, 1, 2, 3, 4. Half of 4 is 2. Here's one of your midpoints for your midsegment. Halfway from 1, 2, 3, 4, 5, 6 is 3. There's another midpoint. And up 4 over 6, no, up 2 over 3 gets another midpoint there. Remember, we're not drawing medians. We're not drawing from vertex to midpoint. We're drawing from midpoint to midpoint. Here is a midsegment triangle. I think that's what you call it. I think that's what they called it. There's the midsegment triangle. Did you need to draw it? I don't think so. They just said find the coordinates of the vertices of the triangle for this triangle. So your 3 vertices here, if I called them DEF, just to give them something. Triangle DEF is what we have, is a midsegment triangle. I don't think I have to do all this. With points D at negative 6, 6, E at negative 3, 6, and F at negative 3, 4. And that's it. Those are the answers that I need there. Okay, yep, 3 midpoints. Let's go into, and by the way, because you probably have more questions, DF is parallel to AC and is half the length of AC. EF is parallel to AB and is half the length of AB. Remember, that's 4. This is 2. DE is half of BC and it's parallel to BC. Cool. All right. Let's go to number 14. Oh, D, E, and F are these letters. Cool. All right. So, but I already used them. How dare you? D is at negative 3, 1. E is at 3, 5. And F is at 1, negative 5. I don't... That might be a right triangle again. It's not going to matter once more, but it might be a right triangle. Just trying to see if I can eyeball my right triangles from where I am. I don't know. Like, where's the right angle? This one might be a right angle. I'm inclined to believe it could be. Okay, it's all about midpoints. You need to find all 3 of them. It's actually kind of a requirement, right? It's not about any 2 will do and stuff like that. You got to find all 3. So from D to E, that slope is up 1, 2, 3, 4 over 1, 2, 3, 4, 5, 6. You've done a lot of 4, 6. So up 2 over 3 gets us that midpoint there, and it looked like that was going to be it. I'm going to guess this is my midpoint here. Down from 5 to negative 5. Yeah, half of that is 0. That's literally what you do for midpoints. You average your values. And then just, 1 over. The one that's on 0 will be it. I think that's an easier way to put it. From negative 5 to 1, that average, negative 5 plus 1 is negative 4. Divided by 2 is negative 2. So it's the one that's on negative 2 right there. Halfway from 1 to negative 3 is also negative 1. So there they are. So these are your 3 midpoints. And if I want to draw that midsegment triangle, it will look like that. But the midpoints are all that matter. And you can tell looks like you have some parallel bits and also half those lengths. So this time I'm just going to write the points themselves. I got 0, 3, 2, 0, and negative 1, negative 2. Great, that is number 14. Okay, let's go to indirect proof and inequalities in one triangle, section 6.6. We got 4 questions out of this one. Let's start with the examples. We have something called, they're going to first ask us to list the sides of triangle ABC from shortest to longest. We have this thing called the triangle sum theorem that says the interior angles of all your triangles will always be 180 degrees. Well, they add to 180 degrees. So if you know 2 of the angles, you can find the third by subtracting them from 180 and you get 50. Now, the reason why we want this angle here is we want to rank the sides from smallest to largest, shortest to longest. Opposite the smallest angle is the shortest side, and opposite the largest angle is the longest side. I don't know how to write a 50 very well here. So if you have a 35-degree angle, opposite that will be the shortest side. That just has some logic to it. Just look at the drawing based on that, if drawn to scale. Opposite 50 would be the next biggest, and opposite 95 would be the biggest. And that's what they're kind of showing there, and they're giving you your list of BC is the shortest, AB is next, and AC as longest right there. You can also do kind of the opposite form. Opposite the longest side is the largest angle, shortest side is the smallest angle. So this one, though, there's no like they add to 180 or anything. So opposite this 5, DF is angle E, that's going to be the smallest. Opposite the 6 is D, and then opposite 7 is F, which is the largest, and that's your answer there. There are other things we can do with these. These are just examples. It's really interesting, I'm just going to say, really interesting how they go about these reviews, saying that like these examples cover all. Clearly they don't, but they're going to ask you questions that probably have nothing to do with it. For example, numbers 15, 16, and 17 have nothing to do with what those two things were, which is always just interesting to see. Describe the possible lengths of the third side of the triangle given the lengths of the other two sides. All right, 4 inches and 8 inches. Now, to not reteach everything, just to state the triangle inequality theorem, the lengths of any two sides added together in a triangle must be greater than the third side. 4 and 8 could be the two smallest sides of a triangle with an unknown long third side, or 4 and an unknown small side, have to be larger than the 8 when added together. Case in point, I'm going to have some unknown x as well. And I got to figure out the different values for x. So I can either, remember 8's longer than 4, right? The small case for x is if x plus 4 has to be greater than 8. The sum of any two sides of a triangle has to be bigger than the third side. So imagine x was one of the smaller sides. If I subtract 4 from both sides, x would be greater than 4 inches, like so. On the flip side, if x was the longest side, 4 plus 8 would have to be longer than it. And if you're not sure what I'm talking about regarding these lengths, definitely check out the video on section 6.6 where I get into this. X would have to be less than 12 inches. This is just going through the inequality. 4 plus 8 is 12, and flip this entire thing to write it like that. As a whole compound inequality, I'm going to write it as such. X has to be between 4 and 12 inches. Any less than 4 inches, even 4 inches actually. 4 inches or less, you can't make a triangle that small because 4 and that other number have to be greater than 8. And if it was 12 inches or more, then the 4 and 8 can't catch up with it in that way. All right, 16 and 17 are much more the same, guys. I don't have to go very long on these ones if you made sense of that one. If you didn't, maybe you will here. A drawing doesn't necessarily help. It can when it comes to just making sense of what you got going the first time, and I'm sure I do that in my other video. Let's consider the first scenario where x plus 6 has to be greater than 9, and the second scenario where 6 plus 9 has to be greater than x. Subtract 6 from both sides, x has to be greater than 3 meters. And combine these, 15 has to be more than x, or x has to be less than 15 meters. So, x has to be somewhere between 3 meters and 15 meters, like so. And number 17, is 11 feet and 18 feet. Okay, x being one of the shorter sides with 11 has to be greater than 18, so x would have to be greater than 7, or 11 plus 18 has to be greater than x, so x has to be less than 29. This is feet. So x is somewhere between 7 and 29 feet. Yeah, a lot of the same stuff here. Not really tricking us. Once you got one of them, you kind of got them all. Just making sense of it. Practice your compound inequalities. That's how we write them. All right, number 18, right. Oh, yeah, indirect proof. Haven't seen these since I did my last video, and that was probably the first time I ever did indirect proofs. I felt kind of not great at them. I felt like a novice. Felt like you guys learning for the first time, right? I had to do it once. Here it was. Write an indirect proof of the statement in triangle XYZ. If XY equals 4 and XZ equals 8, then YZ is greater than 4. Okay, this is going to make use of the triangle inequality theorem here. They're showing this whole thing. This is something that's true, and we're going to prove it by assuming, let's see, how do they say that? What do they say? Let's hypothetically assume the opposite effect. What we're going to do is contradict how the opposite effect can't possibly be true. Therefore, this version must be true. So it kind of works like this. First, let's temporarily assume that yz is not greater than 4, is less than or equal to. I have that symbol somewhere, I think. Yes. Is less than or equal to 4. So I'm doing the opposite of what they're saying. I'm looking at the conclusion that yz has to be greater than 4 and saying, let's assume that it's going to be the other way, if it was less than or equal to 4. Now notice, with triangle XYZ, I think a drawing will help in this one here. I do a triangle XYZ. It doesn't have to look any way particularly. XY is 4. XZ is 8. And this whole unknown, it could be less than or equal to 4, greater than 4, stuff like that. Well, the triangle inequality theorem states that the sum of any two sides has to be greater than the third for all sets of sides of your triangle. If that were the case, this would disrupt the triangle inequality theorem that, I think I have to capitalize it, the sum of any two sides must be greater than the third side, because adding 4 with a number less than 4, less than or equal to 4, where's that symbol again? Less than or equal to 4 would result in a number less than or equal to 8. I'm over explaining this one, by the way. Less than or equal to 8, which is not greater than 8. Of course it ain't. So, therefore, and I forget if the last paragraph has this or not, but that's okay. Therefore, I think I can finish there. YZ has to be greater than or equal to 4. So YZ has to be greater than or equal to 4 because it can't, excuse me, greater than. YZ has to be greater than 4 because it can't be less than or equal to 4. It's kind of how we're saying that. If it was, it would disrupt, dispute. Disrupt, dispute. I don't know how to capitalize these. Okay, that's number 18. I sometimes overtype it because I can type it. You can paraphrase it on your own with that in mind. All right, guys, let's go to 2 more questions here, and then we'll be done. Numbers 19 and 20, but in order to do that, let's look at inequalities in 2 triangles. Get it ready? All right, given that WZ is congruent to YZ, so they mark those, how does XY compare to XW? Well, what you have are 2 sets of sides that will be congruent in these 2 triangles. These 2 are congruent, and by the reflexive property, ZX is congruent to itself. The included angle, the angle in between the sets of 2 congruent sides, compare as such: a right angle, which is 90 degrees, and an 80-degree angle. Because of some of the stuff that you saw in the last set, opposite a larger angle is a longer side and stuff like that. When you have 2 triangles with equal comparisons of sets of sides outside of the angle you're talking about, or surrounding the angle you're talking about, then opposite the bigger angle will be a bigger side over here. These triangles don't have to be fully congruent if those other parts aren't. So XY is going to be longer than XW by nature of the angle opposite being bigger, with all else equal in the side departments that we're talking about. And that's kind of what they're mentioning here. 90 is more than 80, so that measure is bigger than this one. Therefore, XY will be bigger than XW. That's how they compare. It's called the hinge theorem. And that's the way that they go. There's also the converse of the hinge theorem, where you can work off longer sides and note how big or small an angle is. So we have a diagram right here for numbers 19 and 20. I'm going to go and copy, paste it over, see if I can point to it. And these are the last 2 questions we have on here. This isn't everything that we're doing, but it is the review. All right, number 19. If RQ equals RS, and it's labeled as such, and measure, this is not labeled, measure of angle QRT, and I always have trouble labeling this. I'm going to do a kind of double arc. QRT is greater than the measure of angle SRT, make it smaller in a single arc. Then how does QT compare to segment ST? Because the measure of angle QRT is greater than the measure of angle SRT, then the opposite, the angle here, because here's the thing, reflexive property, RT is congruent to RT. That's important that these triangles compare the same way with those sides beforehand. If those sides were different, then of course one side can be different than another. But because this angle's bigger than this one, then the side opposite's going to be bigger. Then QT, the length of QT is going to be greater than the length of ST. That's the conclusion that we make. This marking was important, by the way. Without it, we can't really make that whole statement, but it's there. Now, that is by the hinge theorem. Number 20, it's kind of saying something the other way. Same diagram, but they say if RQ is equal to RS and QT is greater than ST, which is what that other answer was, but this time we know that this is greater than that. And by the way, this is still reflexive property right there, congruent to itself. They say, now how do those angles compare, QRT and stuff? So this was hinge theorem, by the way. What we're about to do is now the converse of the hinge theorem. Opposite, the bigger side will be the bigger angle when all these things otherwise compare in that way. Oh, this already has single arc marks. Hold on. Double, triple, quadruple. Okay. Because I really feel like we're not satisfying everything that's covered in all this. Because QT is greater than ST, then the measure of angle QRT is going to be bigger than the measure of angle SRT. So it's the same thing, but the other way. It works both ways, all given that. This is the converse of the hinge theorem. You say it the other way. All right, guys. Okay, hey. And that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching this one. At some point, I'm going to get the Chapter 6 test and cumulative review up for you guys as well. If you want to check out some more review stuff, check out the other one. It's called Are You Ready? Or something like that. More Chapter 6 stuff. That'll do it. Take care. I will see you in the next one.